So I'm going to record a few podcasts from a couple of nice papers on evolution of the carbon cycle and climate regulation, slightly different than what we did so far in this series of podcasts. Obviously lots of overlap. So I will start with the faint young sun again from this paper which focused on the evolution of a habitable Earth. So it looked more at the evolution of carbon, oxygen, hydrogen escape, ozone evolution, and so on. Let's start with this figure, which is showing the geologic ages here, going back to Hades, Hadean, where there was no life. Earth was still forming in terms of the primordial soup, lots of meteorite crashes, accretion, and so on. Archean, where we have the earliest evidence of primitive life, Proterozoic, which is the early life, and then Phanerozoic, which is the visible life, and thus space is left here for the future evolution of Earth in terms of where the continuously habitable zone where we have liquid water would take us. Obviously, as sun becomes brighter and brighter and the energy received increases, Earth's water will eventually become all water vapor in about 100 million years ago, and then sun would disappear in about 5 billion years ago. We are looking here at the amount of energy that has been produced by impacts on Earth and Moon along the way. So the Moon are the open boxes here, which has had a lot of impacts, and Earth, which has had lots of early impacts and then some meteorite crashes happening all the way into the extinction of the dinosaurs, and maybe even into the end of the last glacial period about 18,000 years ago. And that those energies were sometimes high enough to evaporate the entire ocean. For example, 3,000 meters of water would have been evaporated at these impacts here, and maybe tens of meters at the first big impact. So Moon itself was formed by a big impact that happened on Earth and took out a chunk of Earth and created the gravitationally trapped Moon that rotates around the Earth. So what is the point of this? The point is to look at, let's say, the neighboring planets Venus and Mars in our context, where carbon cycle is again important for explaining the temperatures on Venus and Mars as well as our own planet. So Venus is closer to the sun, much higher energy per unit area, and it lost its water early on, and if water is gone, then no matter how warm it gets, the carbonate silicate cycle, which is the weathering cycle, slows down very much. So the climate regulation or the thermostat is lost. So it has infrared spectra of Venus in CO2 alone, which explains its temperature of 460 degrees centigrade on the surface. So carbon cycle is very important there as well. Mars is not only further away from the sun than Earth, it's also smaller, only about 10% of Earth's mass. So it would have very difficult time holding on to the early atmosphere like Earth would have held on to. So it also has no water in the atmosphere. Maybe there is water frozen. Actually, there is evidence that there is water frozen potentially below the surface and maybe even on the surface in some places. So it also has a spectrum that's basically focused on CO2, and unlike Venus, which had a runaway warming, Mars, with its energy levels and its carbonate silicate cycle being different than Earth's, has gone into a runaway cooling of minus 50 degrees centigrade. So the temperature differences of Goldilocks syndrome on Earth, which gives us the perfect temperature to be in the continuous habitable zone so far, versus the runaway warming over Venus, runaway cooling over Mars, is clearly related to how the carbon cycle has evolved on Earth and been controlling, regulating climate on Earth through its history. Ozone here potentially is a bioindicator as well. So obviously UV in the stratosphere and production of ozone is important for biology as we know it, because RNA and DNA get burned up if the high energy UV were to make it into the lower atmosphere. H2O is critical, explains almost 2/3 of the warming in the greenhouse effect on Earth, but it's a feedback gas, so it's not a forcing. In other words, when Earth gets very warm, water vapor increases in the atmosphere and its greenhouse effect increases, but when Earth gets colder, it drops off, so it becomes colder further. So it's a feedback to how the temperatures are changing because of other factors like changes in orbital parameters or ice ages and so on and so forth. So the questions that arise for Earth then are few. That one is to explain the fact that Earth's temperature has remained basically above freezing throughout its history, which is to be explained because the Earth's luminosity has increased over time, as we saw before. The faint young sun paradox basically says if the sun's luminosity was 30% lower and the energy coming in was much lower, the equilibrium with the given CO2 of, let's say, 300 parts per million by volume and fixed relative humidity would have given us radiative convective equilibrium temperature here, which is much lower than freezing throughout. Obviously that's not the case, and the surface temperature in that case would have been below freezing going back to about 1.8 billion years ago. So the question is, how do you keep it above the freezing point? Because things like zircon, which require water to be formed, tell us that water would have been present in liquid form throughout Earth's history, and there are evidences that there were snowball episodes 750 million years ago and 600 million years ago. So potentially temperatures could have been colder, the entire planet would have been frozen. Of course there are details, because 600 million years ago and 750 million years ago there was life, so and it was most likely in the ocean, so there would have to be light penetrating into the ocean, which means probably the ice was not really ice down to the equator. Maybe it was a slush ball Earth instead of a snowball Earth, but you can read up more on that. But the other point is that biological impacts on the carbon cycle cannot explain the temperature being above freezing beyond a certain point, because first of all, biology doesn't lock up so much carbon, and at some point oxygen was so low that there was no biology as far as we know, especially free oxygen in the atmosphere. And the other thing is that methane could have been present in addition to CO2, and if there was no oxygen, it's much easier to keep methane at a much higher concentration in the atmosphere, and methane would last much longer. Right now methane's residence time in the atmosphere is about 12 years because it's highly oxidizable, but if there was no oxygen, then it would last for tens of times longer in the atmosphere as well. But methane also has to be below a certain concentration, because if it reaches concentrations higher than a certain threshold, then it begins to have what is called a anti-greenhouse effect, because it forms a haze like we have on Saturn's moon Titan, and that would reflect more sunlight than allow in, so it would further cool the temperature. So methane has to be high enough to provide us the warmer temperatures along with CO2, but has to be low enough to not produce an anti-greenhouse effect. But then you have to also find the source for methane. If it was biological, then were methanogens present before we have evidence for life 3.85 billion years ago or so. So this debate is not completely settled. Ammonia was invoked by Carl Sagan, as you remember from the early podcasts, but ammonia easily gets photolyzed by ozone. by UV, and UV would have been high in the early atmosphere because there was no ozone, because there was no oxygen. So then ammonium doesn't potentially is not a player, is not a potential player in the temperatures being above freezing in the Earth's early history of Earth. So all these parameters have to be considered. Then what is the role of carbon cycle? Obviously, even if there was extensive freezing, carbonate silicate cycle is still very critical. So we have weathering where silicate rocks and CO2 in the atmosphere together draw down calcium and bicarbonate and silica into the ocean. The regulation comes from the fact that the ocean crust forms continuously and subducts under the lighter continental crust, and then under high pressure and temperature we have metamorphosis of calcium carbonate and silica, which releases CO2. So even if you had frozen the entire planet, volcanic activity would have been going on, which would trap the CO2 in the atmosphere and eventually would build up greenhouse effect to melt the frozen atmosphere and ocean. So this would give us carbon control regulation on Earth's temperature very early on. Okay, so the evolution of oxygen can be seen here in terms of evolution of life as well. So life, carbon cycle, climate, and Earth itself all together evolved with feedbacks among each other. So even though we always say water is very critical for life, as we know, the geological control on the CO2, oxygen, and nutrients in the ocean and land have been critical as well. So here we are looking at a body volume in log millimeter cube over Earth's history. So going back from the early evidence, the first archaea were there, and the sharp increase in body volume after first eukaryotes would have been associated with a sharp increase in oxygen. So things like Grippania, and then oxygen and body volumes remained at this level here in the scale. It's just a broad schematic scale here. Another sharp increase in body volume just before the Cambrian in the Proterozoic again was associated with the sharp increase in oxygen. So you have things like endocerids, and now of course in the current level of free oxygen in the atmosphere we have blue whales and giant sequoias and so on. So evolution of oxygen is closely related to CO2, evolution of life, and regulation of climate as well. So this is a couple of more podcasts on this angle of how carbon cycle evolved, how it evolved to regulate climate. And this is being developed basically because we want to take carbon cycle and evolution of climate in Earth's history to come to future, to see where we are headed in the future in terms of carbon cycle and what it means in terms of carbon capture and sequestration and utilization. So this is meant for a course called CCUS, Carbon Capture, Utilization and Sequestration. So this little different angle from the carbon cycle we have talked about in the previous podcast is going to be having a lot of overlap with what we've already discussed, but based on a nice review paper from a group that I will show in the next podcast. Okay, so revisiting some of the points, but again, faint young sun paradox and carbon cycle are closely related in terms of explaining the early Earth's temperature and the evolution of atmosphere as well.